I'm Vlastimil. I work at SUSE Labs in one of those core kernel teams, and mostly on memory management. And upstream, I maintain the slab allocator, co-maintain the page allocator, and review and contribute to various other parts of as well. Thanks for inviting me again. I had another opportunity to research and learn a lot myself, and also found out things that are strange, and that now I have to-do list of things I can try to patch. So that's always nice. And what I'm trying to do here is follow up on the talk from last year, where we looked at proc meminfo, among other things, in quite a detail. So if you were here, you remember a slide like this. It has been updated since last year a bit. We've actually removed 2 of the counters that are there, and now they are hard-coded 0. So we don't break any user space parsing them. But yeah, it was this one was an overview of what is kernel memory, what is user space memory, and what isn't, what's in meminfo but doesn't tell you consumed memory, but some other information. And this is even a shorter version than the full thing. So what I'm trying to say now is that why it's useful to know all that. It's often not the whole story when you're debugging some issue. So for example, we talk about how free memory is something that only exists shortly after boot, and then it's filled with page cache, so it's not useful value anymore. Available memory tries to estimate how much of the page cache can be easily reclaimed and used for something else, so that's something better. And it tells you the health of the system at any given moment. It's probably the best single number that we have for that. But when the workload you're running is operating normally, the exact values from meminfo are rarely that important. So, for example, what some people try to do is compare values of those counters on old version of a distro and new version of a distro, which means different kernel and different glibc, and then say it's a regression if some counter increased. And we have to explain that it's not really a regression, but mostly it's due to various implementation details in glibc. The user space memory can be higher, the usage. Kernel does various things for scalability, which often comes at the cost of more memory. Some things like active, inactive LRU sizes are implementation detail, so it doesn't really tell you how your workload behaves, because they are artificial. I will talk about it later as well. Yeah, and for example, if you try to set up limits for memory C groups based on old version or some alerts in your monitoring, and then upgrade, then suddenly you will get out of these limits or get alerts. And yeah, for example, in memcg, new kinds of kernel objects can get accounted, which will contribute to the consumption, but it just wasn't visible before. So what I think matters more than dwelling on exact values is looking at how things change over time, and then you can start asking more useful questions than why is it more than on the previous version. And there are questions such as, yeah, why is this counter growing over time? Is there a memory leak? Yeah, that's a valid question. Why is available memory exhausted? And I see trashing or even OM kills, also a good question. And then you have to figure out, is this a kernel bug, something's leaking memory, or user space is leaking memory, or my workload just processes too much data to fit into my RAM. And when you do this, you need to collect the meminfo in some snapshots over time and look at the trends, but it doesn't tell you the whole story because you don't see what's behind the scenes, what the kernel is doing to keep with that memory load, and that's what the other file, proc vmstat, can tell you, because it counts all the important events that can explain what's happening. Yes, so that's the topic for today. And by the way, meminfo had 60 lines and vmstat has almost 200 lines, so I hope you are not doing anything else today because it will take some time, and sorry to the other speakers. Now, of course, I'm joking, but we heard that there's a 1,300-page book coming up. We saw a print yesterday, so maybe you can look for the answers there. But I guess even that book shouldn't cover in that detail. I wish I could tell you to look at the extensive documentation we have in Tree that is really the reference of everything, but unfortunately that would be just another bad joke because we currently lack such comprehensive information. But on the other hand, it means I can explain it in talks, so that's good for me. So when we look at proc vmstat at a glance, and compare it with meminfo, we realize that while meminfo was somehow created and formatted for human consumption, so we pick what counters are there. There are still more than a reasonable human might need, but at least some effort went there, and the units are all the same, kilobytes. The names are somehow picked and the ordering to make some sense, and the values don't reflect single counters sometimes, but are collected from more counters to give you some semantically useful value. In comparison to that, proc vmstat is just everything, and the kitchen sink. So what that means, it's more suitable for script consumption, and it's just a dump of all the counters we have in the VM in the order they appear in some arrays that count them and just dump the raw values. And the names are taken from another array of very simple text, and they are not trying to be very human-friendly. What we at least do is that because the vmstat collects both state and events, the state counters should start with nr for number and should be increasing and decreasing. And that's also, some of them are used as a backing for the meminfo counters, and others count events since boot and only can increment over time. But since we are talking about the Linux kernel and memory management, this is not completely consistent, so there are exceptions in both directions, as we will see. Some of the counters are internally tracked, not globally, but per NUMA node. I guess we talked about those already in previous talks, and some are tracked by zones. So those are the things like DMA, DME32, which are separate in some of the NUMA nodes. If you know, you know. If you don't, maybe it's not worth learning that anymore, because we hope to get rid of those at some point. And the vmstat is then a sum over all those nodes or zones, but there are also in other pseudo files, like in sysfs, you can see the breakdown per nodes, and in one single proc zone info file, there's breakdown per the zones. And with that, we can quickly just see what are the counters available and how they are internally divided into some sections that have different properties. So we have block of counters that are a state, so these are the NR ones, and there are per zones, and yeah, they are used internally by the page allocator and reclaim, and also exported in vmstat. Then there's a block of per zone events, which are related to NUMA, but not in a way that they would count accesses like NUMA top tool or performance counters, but they count events related to page allocation. I'll talk about that later. They have some per node file that can give you per node stats and can be also disabled, because at some point we realized that collecting them is unnecessary overhead for some use cases, so they can be disabled. Then we have many counters that are per node, and there are both state and events. Some of them are actually duplicating the active and inactive. You can see also here for the per zone. I think that's because at some point where reclaim moved to being zone-based to node-based, we needed to do node-based values without summing them up from zones every time. So maybe we can now remove those. That's one of the things on my to-do list to look for. Here's also some examples of the inconsistencies. So these are events, and they start with an R, and this is a state that can go up and down and doesn't start with an R. Then there's some global state that surprisingly just few counters. There's not much about it, and yeah, most of the vmstat are global events, and these are these contain the most interesting ones. Yeah, and at some point we also removed some counters and hard-coded 0, just to not break any user space, but nobody did that last year when 2 counters were removed, so maybe we don't have to be that careful for vmstat like we do for meminfo, and maybe this one can be deleted. I plan to wait if somebody reports a breakage and then try removing that. So now for the subset of interesting counters. Lorenzo explained the page allocator and many other things, so I don't have to repeat that. That's great. So we have this page allocator for both user space and kernel pages, and we have counters for that when such allocation succeeds. And strangely enough, we do distinguish the zone here, but these are global counters that distinguish the zone differently. They could have been probably per zone counters, but I think for some historical reasons it's like that. I talk about those NUMA events, so they are connected to page allocation, not touching the page. And if the allocation can end up in either on local or non-local node, and depending of what the allocation actually prefers, based on mem policy or some another mechanism, it can be a hit if it's the node it wanted and miss otherwise. Yeah, most of the allocations will be hit on the local node because the default is to prefer the local node, and most time it hits. Page freeing increments a single counter that doesn't distinguish zone, and that's called PG free. And yeah, all the counters count the base pages that form the allocation. So if you allocate 4 pages at once for a large folio, it's not a single increment, but it increments by the number of pages, so it's at least can be compared across different, that is not affected by the folio size, except for NUMA interleave for some reason, so that's another thing I want to look at. So the page allocation might succeed, but eventually the free pages are depleted. And as Lorenzo explained, we have these watermarks that go from lower to higher, called min, low, high. And if we drop below the low watermark, we can still continue the allocation, but we also wake up kswapd to reclaim memory on the given node. And whenever kswapd does its page or reclaim run, it increments page outrun counter and reclaims until it goes above the high watermark. So that gives you some insight into the kswapd activity. Then what it does, it tries to sleep only for 100 milliseconds to figure out whether there's still memory demand. And if something wakes it up because it went again below the low watermark, it increments this low watermark hit quickly and continues reclaiming. If it doesn't get woken up in these 100 milliseconds, but then checks again the free memory and realizes it went below the high watermark, so that means there's some demand but not so high, it will continue again balancing and probably increment the page outrun counter again. So it can be somehow proactive and do work before it's woken up. If nothing, it goes sleep until the low watermark is hit again. Then when we try to allocate and go below the main watermark, which means things are really bad, we perform so-called direct reclaim. So the allocating thread has to reclaim memory on its own and not just wake up kswapd. And there's a counter for that called alloc stall, which again distinguishes the zone from which the allocation was requested. And this can actually be, there can be multiple events if there per a single allocation event, if for multiple alloc stalls because the reclaim might not be successful or somebody steals the memory faster. And sometimes when there are too many concurrent direct reclaimers, we put some of them into sleep instead because they would just content on logs and stuff. And this increments pgscan direct throttle, which, as we will see later, there are other counters that start with pgscan, but they are completely different, so that's something to watch out for. Now, page faults. Lorenzo again explained page faults, great. So when we handle a page fault for whatever reason, either we touch a page for the first time or userspace touches it and it was reclaimed meanwhile, or it was marked read-only, the page table entry, because we want to catch writes for any reason. It increments the page fault counter, and we don't distinguish how large the folio will be in the end. So more effective, more larger folios means more effective page faults. So it makes sense that the number will be then lower per the same amount of memory. Now, if the page fault needs to read something from a swap or file before it can continue because it was reclaimed, it's called a major fault, and we have special counter for that. I was quite surprised that when I boot my KD desktop and run Firefox, the number of these major page faults is just about 10,000, which if each of them would brought 4 kilobyte page, it would mean I only needed 4 megabytes of memory. And that doesn't make sense because just the binaries of everything are larger. And I think that's thanks to read ahead or maybe a combination of read ahead and large folios, because when I touch a page from the file, it will start reading the pages next to it. And then when I finally fault, it's not a major fault anymore because it was already fetched for me. So it's not such a useful counter of what really was needed from disk, but when it starts increasing, it means things are bad. Then, when the page fault needs to write data from swap, there's page swapping. It has also counters for its read ahead that's specific to swap and whether it was successful. All reads via the block layer increment the page PG in counter. The unit is in kilobytes, so it is agnostic to page sizes and everything. But it includes other sources like read syscalls, so it doesn't tell you that everything there was caused by the page faults, but page faults contribute to that. Now, page reuse is a kind of odd counter. It's incremented whenever you have a write-protected page table entry due to copy on write, and one of the parent or child already did the copy on write, and the other now tries to write into the same page and realizes it doesn't need to copy anything because he's the last user, can just reuse that, or where it's a file write shared mapping. Now there are many events related to memory reclaim. For that, first some overview. So we have these LRU lists. Again, Lorenzo covered that nicely. They are split into file, anonymous, active, inactive. This sizing is artificial. That means we try to maintain some ratio that grows with square root based on the whole size. So it doesn't reflect really whether the pages are active or inactive. And what Reclaim does is tries to calculate how many folios from each of the list to scan, and then scans them from the tail where the coldest pages should be. And these events often distinguish whether the reclaim activities from kswapd, direct reclaim, kuhpaged, or triggered from sysfs, that's proactive, and if it's anon or file. And this is maybe best explained on the life cycle of page in memory reclaim. So first we have no page because we have not faulted yet. And then when userspace touches it for the first time, we put the folio, we either allocate in case of anonymous memory or read from the file if it's a file back. We put it in the inactive list and increment these counters that we've already covered. Then when reclaim scan, then the page or folio eventually goes towards to the tail of the list, and reclaim starts to look in at it. So it will scan it, but incrementing the page scan counter, but sometimes it will not be able to isolate it, or maybe it's from the wrong zone, which increments the PG skip counter, and it's put back to the inactive list. If it succeeds the isolation, it's again the page scan counter is incremented, and then it checks whether it was last access since the last scan, looking at the page table active bits, and if it was, it marks it as referenced and puts it back on the inactive LRU to see whether that was just a one-time access or there will be more of them. There's no counter for this particular action. Now, if the folio was already accessed and already marked as reference, it means it's used a lot, so it's put in the active list, and there's PG activate counter for that. Otherwise, if it was not accessed, then even the reference bit doesn't save it, and we reclaim it, increment the PG steal counter, that's the counter for reclaim, and PG free because we eventually free it as well. Now, if it was, there's a special case if it was previously marked by medvice free, and that has PG lazy freed and instead of the PG steal, but otherwise it's the same. Now the new thing is we have memory tiering, so if there is a NUMA node that's considered the lower tier of the current node and it has enough space, instead of reclaiming the page, we might put it on, migrate it to that other node, and there's a counter PGD mode for that. For some reason, it also increments the PG steal, which I think is a mistake, because initially there was no PGD mode counter and it was PG steal, and now there's the counter. It doesn't make sense to say it was reclaimed when it was just migrated. Now on the active list, when reclaim eventually looks at the active list too, the action of scanning the active list is not called PG scan, but it's called PG refill, which is not very intuitive, but it is what it is. And again, what can happen is it might not be isolated, so it goes back to the active list, or it is isolated and increments the PG refill as well. And again, we check whether the folio was accessed in the last scan, and the reference flag doesn't matter here anymore. That's only for the inactive list. And if it was accessed, we put it back. There's no counter for that. If it wasn't, we put it on the inactive list, and there's PG deactivate for that. So that's the main counters for reclaim. There are some related ones for write back. So when the reclaim can only reclaim clean pages if they contain data that's not stored somewhere on disk. It cannot be just discarded, with some exceptions. So if it's anonymous, we have to swap it out, and that increments the page swap out counters. If it's file backed, I think we currently don't do write back of dirty file folios from reclaim anymore. That's done independently with some flusher threads, but reclaim might still encounter a folio that is dirty, and now it cannot reclaim it because it would have to be written back first. So what it does, it only marks it with a reclaim flag and puts it on the active list. And why is it on the active list? That sounds counterintuitive, because then it doesn't encounter it again during the scan of inactive list. So that's just to put it away, because I cannot do anything with it. And it also increments the page activate counter, which is strange, because it's technically moving it there, but not for the reason that it would be active. So another strange thing. And that can happen even in swap, because even when we initiate swap, it might not be synchronous, but that means it's not completed immediately, so we have to do something with the folio meanwhile. And now the trick is that when the write back finishes, or the swap out, the handler of the write back will see that we've set the reclaim flag there, and what it does, it immediately takes it again away from the active list and put it to the tail of the inactive list, because now the folio is clean and reclaim can immediately see it and reclaim it on its next scan of the inactive list. And that increments PG rotated counter. Now, like we have counter for reading from the block layer, there's PG out for writing. Again, write back and swap out is only part of that. Now there are counters related to something called working set detection that are a bit more tricky. So just a high-level overview. Imagine you have a lower end system with only 4 or 8 gigabyte RAM. You run Firefox, it fits well, but now you want to start LibreOffice, another large application, and they don't both fit well in the memory, but each of them alone would. So what happens with normal reclaim is that because we tend to focus on the inactive list and make it small. The LibreOffice might be trashing itself because it has too many pages for the inactive list. It would be enough for the whole memory, but for the inactive list it's too large. It will keep reclaiming itself, and it takes time for the system to recognize that, yeah, this Firefox is actually not being used now, so I should reclaim it and let LibreOffice be the new working set or the active memory user. So the trick here is that we remember when folios are reclaimed, we track it in something called shadow node, and remember time when we reclaimed, and when we page fold again such a reclaimed folio, we can know how long in the past it was reclaimed. And then we can do some math to estimate whether, yeah, so it was reclaimed recently. If the inactive list could be as large as the whole memory actually, then it wouldn't be reclaimed in the first place. So that means that's the new working set, and we should instead make the page activate, put it on the active list immediately. Yeah? So it would be like, yeah, if you killed the Firefox first and made enough memory for LibreOffice, then you would get the same result, but it's able to recognize that the Firefox is now not used and it should push it out faster thanks to tracking some extra data for folios that were reclaimed. So when it reads back a folio that in a fold that was previously reclaimed, so we have already a shadow entry for it, it increments this refold counter. If it decides that it was soon enough after reclaim to be active, it increments this counter, and there's a third counter for a special case of this when the folio was already active before. But the semantic of that is not that easy, and it's used internally to calculate some reclaim costs. And yeah, we also track how many nodes we need in Xarray just to store these shadow entries, and whether sometimes they need to be reclaimed because we are occupying some memory to make the reclaim of the other memory more effective. So that's the trade-off here. So and that was the last counters I covered. And now the conclusion is that these really are able to provide you insight into what the subsystems are doing. So if you get the reports such, my system was slow and I think it was reclaimed doing something, or kswapd, kcompactd takes too much CPU time, why? Or my favorite one, swap usage increased even though there was free memory and now it's not decreasing. So your kernel is buggy. So to answer these things, the absolute values are, again, not so interesting. So what we do is take snapshot every 10 seconds, for example, and see how much they increased since the last snapshot and how many of these events occur per second. Yeah, and I'm not giving you exact recipes here because you learn by doing this. But of course, knowing what the counters exactly do, and it's not always obvious, it's necessary to start somewhere, and that's what I try to explain today. But broad, while not a recipe, just a broad example of how I would approach this swap usage increase even there was free memory. So we have to take snapshots of both meminfo and vmstat, and yeah, if you see that the number of the free memory decreased during the workload operation and then came back, then you can already say, yeah, you say there's free memory, but there wasn't free memory at some point where it mattered, so we did not swap out just because we could. There was really memory shortage. And in that moment, we should see the page swap out counter increasing. And the other question I would ask or check whether we have very low page cache and anonymous memory was occupying everything. And if yes, it means that the workload was just too big and we couldn't do anything else to swap it out, so it's not a bug. But when it wasn't that bad, but we saw working set activate file increases, it means that the mechanism worked and it detected that some of the anonymous memory is actually colder than some of the page cache. So it makes sense to swap out these cold anonymous pages. Yeah, but people are used to like swap is bad. We don't want to see any of it used. But the implementation changed to use it more smartly. So that's not a bug. Yeah, and to confirm that the memory was really cold, we should see no page swapping events followed by the swap outs, because there's cold memory sitting in swap, nobody touches it. So I didn't cover many other counters, but I think I covered the main ones. The other ones are either quite straightforward or obscure and not worth covering. It's not, again, the end of the story when this granularity of counters doesn't give you enough information to debug your bug. There's always tracing. Many of these events happen in some place where, or are incremented in some function where next to it there's a trace event that collects more details about it, so you can enable that. But then you have more data to post-process. But we have timestamp of each event, which process context, and what were another properties of that event. Even lower level, you would have to use Dragon debugger or start adding print case in the kernel, and then you can observe everything, but then you need to really know what you're looking for. Okay, so that's all from me. Thanks. Any questions?
Hello. Okay. Yeah, thanks for the presentation. I have a question about so is there a way to completely prevent that a task gets some pages unmapped, remapped, or reclaimed? To give some context, let's say one example is okay, I can unlock the memory, of course, and that in theory should prevent this unmapping and remapping. But one thing is, for example, the VM unevictable allowed, which is or compact D unevictable allowed, something like that. Because compact D can still unmap and remap pages, for example. And probably transparent huge pages is another thing that can unmap and remap pages. Or memory reclaim is probably, there are probably under memory pressure, I mean, some pages can still be unmapped and remapped.
So as far as I know, there's only the mlog for specific pages. And you can, with that sysctl, you can also control whether it can be migrated. If you have a real-time workload that can be a bad, even the migration. And you can disable swap, but completely prevent, no. But you can use memory C groups to prioritize some things against other, and if you set it up correctly, then it may prevent some particular things to be reclaimed. So
because disabling the it's compact and evictable allowed. Disabling that helps me a lot to reduce a lot of corner cases, but this is quite important for user space scheduling, Because if you have, like, if with SCADAX, if you have a user space scheduler that runs critical component that, let's say, tasks are in a queue in user space, if you have a page fault, you need to run a K-thread to resolve the page fault. But if the K-thread cannot run because it's in the queue, then there's a kind of a deadlock, which is not about deadlock, just the scheduler exiting because of the core SCADAX. So, yeah, anyway.
Yeah, so maybe memory C groups wouldn't be enough for such a thing.
Yeah. Thank you.
I have one question for you. The CPU topologies are evolving a lot, meaning that we have now packages that can have up to 12 or even 16 NUMA nodes per CPU package, meaning we can have more than 30 NUMA nodes per host. Do you have any hint to prevent a task from getting memory out of its local NUMA node memory?
Yeah, you can use mbind. You mean NUMA nodes?
Yes.
Yeah, so that's mbind syscall or some of the tools that will wrap this in. If you don't need to want to modify the binary, there are some tools that can wrap the execution of it. So,
okay.
So that's the answer: the memory policies or CPU sets.
Okay, thank you.
So you mentioned some typical problems that people have, and you mentioned some counters that one could look, or counters that one could look at over time to understand those problems. Are there any tools that will choose the right counters, make the right graphs, and show you things that are relevant for particular problems?
Yeah, I don't know any, because the problems are often in some sense unique, so any tool that would try to do something generic could give you a misleading result. For example, what we do, we include the SAR package in every distro, which collects the counters on background, a subset of them, and only in 10-minute intervals. So we have something to look at even when in the initial bug report, before we tell the user to collect something with more granularity. But automatic tools, I don't know. Yeah. It's always by hand.
Okay, thank you.
I have maybe a meta question on this talk when you prepare it, or the previous one. You showed there are a lot of incoherent interfaces. Do you want sometimes to fix them? Because I know it's part of the UAPI. So do you want to fix those counters that are not the proper units or not declared properly, or do you want to update the documentation? Do you usually do changes when you prepare such a talk?
So yeah, I would like to change those cases where I think it's wrong, and it will of course lead to discussions whether this new semantic is better or not. And yeah, it will be a user visible effect in the sense that the new kernel will behave differently. But yeah, it should be acceptable in this case. Or maybe I missed your exact question.
Yeah, but my main question is, did you do such changes when preparing talks? I mean, in general.
No, for now I just took notes. But for example, after the last talk last year, I noticed that counter for bounce buffers, now write back TMP for fuse become unused, but the author didn't remove it completely and put the hard-coded 0 there, so I did that immediately based on preparing the last year's talk. So something like that will happen now. So.
To follow up on this question, I know you've probably already thought about that, but anyways, I'm going to say it out loud. Why not having versions of the metrics? If you want to make something evolve, not breaking it, just you maintain the old one and you offer a V2 or something like that?
You mean versions of those counters? Or?
Yeah, with different names or whatever.
Like, how would you maintain your own, like downstream or?
No, like, let's say something stupid, vmstat /v2.
Oh.
That would allow you to rename and have a maybe more coherent.
Oh, yeah, I understand. So, yeah, when a syscall got a 2 version, it means it's really serious reasons for that, and I think there would be resistance to do that for vmstat, because even if we promised, like, we made some mistakes before, we cannot change it, and now there's a new version and we won't make mistakes, but eventually we would again. So yeah, eventually you would have 2 files with some subtle mistakes. So it's better to hope that, like, we don't want to break user space, but the consumers of this maybe should know what they are doing enough so they can update their tools and will not insist on, can you put the old semantics back because I cannot change it. So with files like these, there's hope that changes can be possible.
And there have been some changes already, fixing some bugs. So if you're running an older kernel, you're going to see a different behavior. That's already a thing. So.
Yeah, the Linux rule isn't like you cannot ever do this, but if it breaks someone, you cannot do this. So if there's no someone reporting it's broken, it's fine.
Thank you.
Thank you.